Hey, we're going to take on part 3 of this video. Parent conferences for my kids just got booked. Good deal. We have exponential functions to solve, and I think and then one more log function to solve, because I did the first two on the previous video. Of course, the whole PDF is uploaded for you. Now, to solve an exponential function, you can see that we're dealing with something that's some kind of exponential, something to an x of sorts. Excuse me, you want to isolate that, just like we did with the logs, get away things that you can get away with old algebra methods, inverse methods, divide by 3, for example. So 2 to the x minus 1 equals 4, add 1 to both sides, and we're sitting here at 2 to the x equals 5. This is where you come in and you do the inverse operation, which you can choose your favorite log. Now, some will tell you use log base 2, but I think in the end, it kind of makes more work, especially since sometimes we're going to turn to our calculator anyway. I always just choose natural log. It's just my go-to log. Take it to both sides, which allows me to pull the x out front. So that's what I do it for. So I get x ln2 equals ln5. ln2 is a number. I may divide both sides by ln2. It's not ln times 2. It's just ln of 2. It's its own full value. It's an irrational number. That's it. I have just canceled my ln of 2 on that side. I get x equals ln of 5 over ln of 2. That is an exact answer. If you want the decimal approximation, put it in your calculator. But this will do. This is the result. X is natural log of 5 over natural log of 2. You can write it as a single log if that makes you happy. With our base change formula, you could call it log base 2 of 5 if you wanted to. Okay, on to the other side. There is a log equation to solve. Now this one has multiple logs in it. Well, this is where it becomes advantageous to notice that we have 2 logs of the same base being added. I got a thing for that. I can condense those. So where you can condense, do so. If you have many logs, you have the same base, make 1 log. I'm just going to do the left-hand side. These are added, so I'm just going to do x times x plus 8 and put them as a single log. Remember, you can multiply them inside 1 log. When you condense, you don't write additional logs. You take multiple and make it into 1. And this guy over here, this log 2, 3 log 2, I'm going to make it log of 2 cubed and take advantage of that. That's kind of slick. Now we can go on to do to both sides of this thing what's called exponentiating, where I can kind of cancel out the log of both sides. I will do that in just a minute, but it's also nice to note, if you can see, that the inside of this one and the inside of this one are all I need to compare, because it's log of something equal to log of something. Those somethings must be equal. So x squared plus 8x, that'll be there. And the inside on this one's 2 to the third, which is 8. And we can go on solving this quadratic any way we want. The other option, I'll just do it in purple here and let you just look at it and don't need to necessarily write it. I could have, noticed this is log base 10. I could have exponentiated both sides to the 10 power, cancels this log out, and I end up right back in the same place I was. Okay, so I solved that one. So I put this in here. You can see I hear my phone ringing. I'm going to hold off on this. X squared plus 8x minus 8. Set it all equal to 0 like I do with any good quadratic. And then from there, I can do quadratic formula or factor. I'm going to do quadratic formula just real fast. X is the opposite of b, plus or minus the square root of b squared minus 4ac. And I'll call that negative 8 all over 2a. There it goes. So 64 plus 4 times 8 is 32, square root of 96. And it's not particularly pretty, but you get the idea that you have your 2 solutions. Square root of 96 is left all over 2. And we could go on from there and simplify if you felt the need to do so. But at this point, I just wanted to give you the idea of we are solving for x. This has 2 solutions to it. But the process is condensing logs, if you can, comparing their insides, or exponentiating to get rid of logs. Do the inverse operation is another thing. And we also have solving a quadratic. Anytime you see one, you have to set it equal to 0 and either factor or do the quadratic formula. All good things that have to happen. Down below, so now we've finished up that sheet. We're going to use those skills of solving that we just finished with to do a couple of these cool modeling problems. And so, for instance, the basic models that we deal with, and if you haven't ever written these somewhere safe, you want to do so, there's basically two we're going to work with. We have growing in spurts, compounding problems where you have n compoundings that take place. And I'm going to give you guys finally a little sheet that kind of makes this a little bit easier. Let me pull it up here where you have those. There's the formulas here. Feel free to record them somewhere, but I'm just going to hand them to you so you can kind of stick it to something. Wouldn't it be cool if I could put a sticker to it and you could stick it somewhere? But those are the basic formulas that we end up using for our purposes. There's the continuous version, and there is the compounding n times per year. And there's one other that I'll talk about, which we'll do in problem number 11. So we'll go with that instead, okay? So shall we? Let's put this to work on a couple of these, and we'll roll with it. Okay, I'm going to do 425,000 on the first one, 4.2% compounded per year. And that one is a yearly deal, so it just needs the model. So all we do is P equals 425,000. 1, 2, 3. And I squished it in there, didn't I? And it's 1 plus, I'm going to go ahead and just delete the stuff that I wrote before because I forgot to write that. Sorry about that. And 1 plus, and the interest rate 0.042. Make it a little bit bigger. 4.2 over. It's happening yearly, per year. My compoundings is 1 time per year. Now this is emphatic. I don't need to put the 1 in there. But I just want you to know that one formula that we have is all that we need for doing those compoundings, even yearly, if that's possible. The second one is continuous compounding, which I'll show you use for that in just a minute. Okay, and then the next one is, hey, predict the population in 5 years. Use that formula, plug 5 in for time. You've got this thing, and I'll leave you guys to find that number, but that second one, you just put 5 in for t, and you're home free. And I think I'll let you just live with that piece all by yourself, okay? Then down below it says, when will the population exceed 750,000? The word exceed plays a little small role in it, so just keep track of the fact that we did say exceed. And when you set 750,000, this will get us into that solving thing we just got done with, 425,000. And we're doing 1 plus 0.042. I might just write that as 1.042 at some point to the t. This problem is, well, what year will this happen? That means I am going to be solving for that t up in there. So as I keep after this, you remember I need to isolate the exponential is what I need to do. Okay, so we take and divide both sides by 425,000. Take that, divide it away, 425. Bingo, bingo, bingo. Divided by 425,000. Got it. Cancel those things as best you can. And what I end up with is 750, if I want to cancel some zeros because I like to, for 425 is equal to 1.042 t. Okay, that's the part where we go, all right, what do you do now? It's an exponential function. It's isolated. I can jump in and take the log of both sides. So log of that whole thing and log of this whole thing. Oops, I guess I can put the parentheses around both ends there. That's the story. The reason that becomes advantageous is because I can bring the t out front of the log when the moment comes, and I'll do that right now. Okay. So ultimately, I get the log of 750 over 425. That's one log, by the way. Don't put another log in there. It's easy to think you want to do that. Is equal to t times ln of 1.042. And so then you can take and isolate t by dividing both sides by that natural log of 1.042. And we are home free. Got it. This is equal to t because we've canceled away it on the other side. It's an exact answer. Your calculator spits out a decimal. That'll be handy when the time comes to look at that, okay? Now, I want to get to one more problem. 2 if I can stomach it. I'm going to try and make it as fast as I can. But there's 2 more kind of models that pop up. One, this is a slightly different one. When something doubles in a known amount of time, it's a little bit different. It's not our traditional growth model. It's not the it's not the continuous growth model. It's not the growth at certain compounding periods. This is its own little issue, and we talked about it in class if you were there. And Doubling actually is 2 to the t by itself. If you want to take, I have 5 amoeba to start with. It will double in so many days. The problem is if I just put 4 in there as is right now, and put a 4 right here, it actually makes this 16, and that's too much. I don't want to take 16 times 5. That's not doubling. That's too much. So I only want it to double once time is 4, and that's where there's a little compensator, 1/4, that gets put in front of that t. This is the setup for any type of doubling type of problem. The formula is p naught, so for doubling. And if it were tripling, we'd put 3 inside the parentheses. If it were halving, we'd put half in the parentheses. All follows the same process. But there's this 1/k times t that happens, and that k inside there is how often it doubles, how many t's until it achieves the growth factor that we have inside that. How many t times until the factor is achieved, so in this case doubling. Okay, so that's what we put in there. Every 4 days means 1/4. Every 10 days would be 1/10. Every 150 days would be 1/150 would go in front. Okay, there's our little model that goes with it. Ours has a 1/4 in front of the t, with the 2 being the base because we're doubling. How many amoeba after 10 days? All right, we put in, we'll find out 5 times 2 to the 1/4, and we're going to plug 10 in. Done. You'll find it in your calculator. It'll be great. When will the population reach 10,000? You set our lovely model equal to, this has got the whole 1/4 t going for it. You're welcome to write it as t/4 if you like. Okay, I might do that. That's my formula. The when means what time. I don't have, but you're recognizing now an exponential. You got to isolate it. Take the log of both sides. That 5 needs to go. You divide by 5. 10,000 divided by 5 is 2,000. And if I set it equal to 2 to the t/4, then I know now it's time to log both sides to get that exponent out front. And to drive it home, we are left with none other than the log of 2,000 is equal to t/4 times ln of 2. Now, thing is I got to get t by itself, so a couple steps you can take in no particular order, but I'm going to divide by natural log of 2, divide by ln of 2. These are separate logs, and I need a little room to borrow it down here below. But you end up with natural log of 2,000 over natural log of 2, and that equals t/4. The last step, multiply both sides by 4. And you are done. There is your result for t, because these will cancel. Put it in your calculator and roll. There you go. Continuous, I want to do one example of those, and then I'll just upload. I'll get to the next video a little bit later. But remember, your continuous interest means you're using the PE to the RT. So your formula will be 12,000, your initial amount, E to the 0.035 T. When you want to do the 5-year one, you're going to put 5 in for T and call it good. Okay, next video will come with the rest.